test instruction where I also post this instruction inside e-learning portal, so you can have a look at it. Maybe you need to go through in order for you to really understand how the test will be conducted. Okay. All right. What else? I think that's it for the information. Okay, we proceed with our lecture today. Right. As I mentioned earlier, first we're gonna have. Okay, before we proceed, I have some info to let you guys know that I plan to stop our session a bit earlier today, around 10 or 10:15, because I need to attend a conference, video conference. So I really apologize for that one. Maybe we will continue. I don't know until which part. I think maybe we will continue our lesson in on Thursday. All right. That's info for you guys. All right. For week 6, first we're gonna have a look at what is inductor and capacitor, and then we will have a look at circuits involve combination of resistor and capacitor, as well as resistor and inductor. And here I also mentioned about source free and step response, means that source free, meaning that the circuit just involve components, passive components, for instance R and C or R and L. You don't have any source inside the circuit. For step response means that source voltage source or current source is kept intact in the circuit during the analysis. So we're gonna learn about two types of solution over here. One is source free, another one is with source or step response, RC and RL circuit. And this is something which is really important for you guys to master, or for you guys to know how to analyze the circuit, because it will be asked in final exam. One question will be asked in the final exam. One question means that if question number 2, for example, 25 marks, first part for first order circuit maybe contribute about 10 to 15 marks. So it's really important for you guys to know how to answer question involving first order circuit. An overview of passive component. Passive component, we have here resistor, capacitor, and inductors. Last few weeks or last 5 weeks, we discussed about resistor, where if we talk about resistor, it involves energy dissipation, energy dissipation in terms of power. Power dissipate at resistor, blah blah blah, something like that. And for the other two passive components, capacitor, for instance, capacitor didn't dissipate energy; it stored energy, and it stored using or in terms of electric field. On the other hand, for inductor, also storing energy. However, it is in terms of magnetic field. So that's something which is a bit different if you compare capacitor and inductor. Both, I know both are storing energy. However, one in electric field, another one in magnetic field. Okay, this is important definition throughout the chapter or throughout the topic, where you need maybe this definition is something new for you guys. Maybe this is the first time you heard about transient. Maybe it's first time you heard about steady state and so on. Okay, what does it mean by transient? Transient is a momentary variation in in current, voltage, or frequency. For example, if you look at these two response, the response here where you have variation of voltage, for current at here is considered as a transient phase, where you have um, variation of parameters or variation of values over here. However, for steady state, what do you mean by steady state? A state or condition of a system or process, such as one of the energy states of an atom that does not change in time. So the second phase over here is considered as a steady state response. Ideally, we should have something which is constant over here. However, if you look at the response of capacitors and inductors, the steady the constant value should be towards the end, towards t towards infinity. So here is still something which you call it transient response. If you want to be very ideal. However, it also can be considered as steady state phase at this part, because it's approaching the constant value. So if you, this is something I think it's a bit similar. However, this is a loading response. This is unload response, where loading means that we start from 0 up until our maximum value. This one is starting from 0 up towards our minimum value. So this straight line part is considered as steady state region. The one that varies over here, the value that variation of values over here is considered as transient. Then goes to the unloading part. All right. Another definition that you will come across very often in this topic is switching condition. Switching condition means that in your circuit, you might have a switch over here, and normally it's labeled like this, labeled like t equal to 0, and you're going to have arrow like this. Means that the switch will be closed at t equals to 0. So in terms of switching condition, let me get back into the definition. In terms of the condition, we're going to have a three definition of switching condition. First is t less than 0. T less than 0 means that we're going to have, it means instant before the event. Okay, if you compare with this diagram, at t less than 0 means that the switch will be open. Okay, and t equals to 0 means that initial condition, and referring to this one, t equals to 0 means that the switch start to close the circuit. And at t greater than 0, it's the instant after the event, means that the switch is kept closed, and we have a look or we try to analyze what's going on inside the circuit when when the switch is closed at t greater than 0. Okay, that's important definition. This kind of these three definition you will come across very often in this topic. All right. What is capacitor? Okay, this is the symbol of capacitor. We're going to have a fixed capacitor, looks like this, a symbol of fixed capacitor. symbol of polarized capacitor, which is we're going to have polarity on the capacitor, and also symbol of variable capacitor. And the physical look of capacitor is something which is look like this, where you're going to have something or components which unit as labeled as microfarad, nanofarad, something like that. Micro F means microfarad over here, and F means nanofarad. So that is the capacitor. I think everyone knows about this. It's basic physics. And what does this capacitor do? It will steadies the voltage in our circuit. If you think about voltage regulators or uh, your, in fact, your power, not power bank, the adapter, handphone adapter, charger, also involve capacitor inside that. The main component is capacitor. You try to steady the voltage, and as well as of course lah, if you try to drop down from higher voltage to lower voltage, you try to use transformer, but the transformer voltage response is a ripple voltage response, and to steady the voltage to a constant value of maybe 5 volts, 10 volts, you need capacitor. Okay, that's a bit of capacitor that steadies voltage. And if you look back earlier, we know that the capacitor will stores energy in terms of electric field. Okay, how does capacitor behave during transient? Okay, during transients, this is what happened to voltage across capacitor. It will increase from 0 to the maximum voltage of the capacitor that capacitor could be. And the maximum, if you look at this, the circuit, it should same as the value of this voltage source. Means that the maximum voltage over here should be, for example, here is E. If the voltage here is 10, means that the value over here should be 10. So that's how voltage across capacitor looks like. If you remember, last time we learned about resistor. Resistor, if a current is flowing through resistor, the response should be, for example, this is a short circuit. For example, this is a wire. There's a wire over here. We have a single resistor over here. And if you look with respect to time, and maybe this is VR, okay, the response of VR always giving us a constant value like this, constant value, which is the constant value over here is E, because voltage drop across this resistor same as the voltage supplied by the voltage source. So the difference between resistor and capacitor is that capacitor try to build up the voltage. The phase where the voltage build up is given by a transient interval. So for resistor, we don't have any transient interval over here. However, for capacitor, we do have transient interval. If the voltage looks like this, and how about the current? The current will behave like this response. Means that with respect to time, the current is given by a value of maximum value and decrease towards 0. So this is the transient interval for capacitor. So it's starting from higher value or maximum value of current that possible highest value that this circuit can give, and decrease up until 0 ampere if T towards infinity over here. Okay, right. Now that's what is meant by transient interval. And during steady state, okay, since you already learned about steady state just now, means that the interval over here considered as a steady state. Okay, this part is considered as steady state as t towards infinity. And during steady state, what happened to the capacitor voltage, or what happened to the capacitor in general? If you keep this circuit being running all the times towards infinity, the capacitor will behave like an open circuit. Okay. During open circuit, we know that voltage across here should be equals to voltage over here, and current flowing through here should be equals to 0. That is, this definition explain what happened in these two circuits. If you look at these two circuits during transient interval, okay. However, for the steady state, during steady state, as the voltage reach its maximum value, voltage across here, okay, voltage here, V equals to E. Okay, voltage across this open circuit equals to E, reach its maximum value, and the current over here leads towards 0 value. I equals to 0 over here. So that's what happened to capacitor during steady state. It's because of the capacitor will behave like an open circuit. So current will be equal to 0, and voltage will be the same as what you seen from the voltage source, considering this is the circuit. Okay, that's for capacitor. And for inductor, the symbol is, this is the symbol of inductor. Maybe we're going to have fixed and a variable inductor. What's happened in inductor is something which we can consider as the opposite thing that happened in capacitor. So in capacitor, we know that it steadies the voltage. However, for inductor, it steadies the current, and the energy will be stored in terms of magnetic field. So remember, for capacitor, steadies the voltage. For inductor, steadies the current. And if you have circuit looks like this, okay, and the current and the voltage will behave like this one during the interval, transient interval. Okay, and if you look at earlier, the voltage try to build up from 0 to its maximum value. However, in circuits involve inductor, the current will try to build up from 0 up until its maximum value. And its maximum value is given by V over R, or maximum value current flowing through here. And the voltage drops from its maximum value, or from E over here, Vs or E, drops until level of V equals to 0. However, this is considered as the picture here tell us about transient interval. If you extend the response, okay, towards T towards infinity, you will see that the current will steadies or build up from 0 to a steady its maximum value, and for voltage from maximum value drops until V equals 0 over here. Okay, that's relate with what I'm trying to explain here. So you know that this part is steady state. This maybe I put like this. This part is considered as steady state, and if you keep supplying current, and if you keep supplying source voltage and or current in the circuit, for example like this, and you observe time towards infinity, the circuit can be considered as as reach its steady state, where at steady state condition, this inductor will become a short circuit. And remember, if this is short circuit, means that voltage across here is equals to 0 from here to here. That's why V short circuit here is 0 volts. And the current over here, I short circuit here is given by E divided by R. So this is the maximum current that I mentioned earlier, Vs, or E over R. That is during the steady state condition. So it relates back to what we have learned in previous figures. So in previous figures, we know that during steady state, voltage will have a maximum value. Current will have its maximum value, and voltage will have its the value will be equal to 0. So that's tells by this circuit arrangement. During steady state, or if we let the circuit run towards t towards infinity, in other words, if we let the circuit for a long time, the voltage across the inductor, or the inductor itself, will behave like a short circuit, and the voltage is equal to 0, and the current flowing through the circuit consists of resistor and inductor. The maximum current will be given as E over R. Okay. In summary, this is something with the table here is very important. So you need to know all these things. So I've already highlight which part is very crucial, and for me, everything is crucial lah. However, that's the thing that you always need to know throughout your studies. I think not only in year 1, maybe up until your final year. You need to know that the capacitor, the current in capacitor is given by this equation, C dV over dt. dV, V is the voltage across the capacitor. The current is given by value of capacitor times the rate of change of voltage across the capacitor. And for inductor, the voltage is given by L di over dt. Okay. This is the easiest equation that you can remember, compared to if you try to have a look at the voltage across the capacitor. Is a bit complex, because we're going to have integration over here. All right, for the energy stored, energy stored for capacitor and inductor, both using the same form of equation. The first one involves voltage, where for capacitor, if you would like to calculate the energy stored, use 1/2 C V squared, and V over here is the voltage across that capacitor. And for inductor is 1/2 L I squared. I over here is current flowing through the inductor. And I think this part is very important in terms of how capacitor behave if we have a DC supply connected to the circuit for a long time, i.e. at the steady state lah. During steady state, you should know that capacitor will behave like open circuit. And for inductor, it will behave as a short circuit. That's very important. Another one is about variables that cannot change instantaneously. In other words, variable, if you have a variable in the circuit that cannot be changed instantly or abruptly. For capacitor, voltage cannot change abruptly. However, for inductor, current cannot change abruptly. It will follow the transient interval. I mean, there's loading and there's increase of voltage up until maximum and decrease of voltage up until its minimum value or zero value. So it cannot change abruptly. For example, if you'd like to change the polarity, voltage polarity across the capacitor cannot change abruptly. Same goes to inductor. Inductor current direction cannot change instantaneously in RL circuit. All right, I think that's just an introduction lah about capacitor and inductor. Our main topic is yet to come. Okay, this is what gonna happen in our main topic. The topic that I would like to share today. We try to examine RC and RL circuit response in DC circuit. So something which looks like the circuit that you looked earlier. We have DC voltage source and R combined with capacitor or R combined with inductor. That kind of circuit arrangement can be considered as first order circuit. Later on, we'll try to have a look at what does it mean by special function. For example, a step input, unit step, unit impulse, unit ramp, where this kind of special function will be used in step response of your first order DC circuit. Means that this is the source that we try to put inside our circuit. In this topic, we will learn about a source-free first order circuit as well as switch source. Okay, switch source means that we're going to have a source or a voltage source in our circuit during t greater than 0. Okay, this is a glance of what's going on. Source free with source in our circuit, source free and also circuit with source. And we try to have a look at RC and RL in our circuit. Circuit consists of our combination resistor and capacitor, resistor and inductor. We try to develop RC or RL equivalent circuit using Thevenin theorem. So in this topic, we will use Thevenin theorem a lot. Maybe if you try to use Norton also can. However, if you use Norton, means that you need to come up with I Norton. If you use Thevenin, you need to come up with V Thevenin. All right. Later on, we try to get to know what does it mean by initial value and also time constant and the way how do we calculate that one. Maybe sometimes initial value is given in our question. However, in other question, maybe you need to find what is the value of the initial value or voltage across maybe capacitor or current flowing through the inductor, the initial value of that, and the way we calculate time constant. Later on, we try to come up with voltage and current response of the DC circuit equation. All right, I think I've already discussed this one. The first order circuit is characterized by first order differential equation. If you have a derivative in your equation, means that it's considered as first order circuit or first order differential equation. And also we're going to have two types of first order circuit. First called as RC and second one is RL. We have two ways to excite the circuit, either using initial condition and one more is using independent source. Independent source maybe step response, special function that I mentioned earlier, maybe using independent voltage source, independent current source, maybe, right? For RC circuit, source. So now we move on to look at what does it mean by source-free RC circuit. Source-free RC circuit occurs when DC source is suddenly disconnected. Okay, disconnected from the circuit. And energy stored in the capacitor is released to the resistor. And if we consider this kind of circuit or series combination of resistor and initially charged capacitor as shown, okay, how do we analyze that one? Okay, first, before we get into the calculation, I would like to remind you guys here, since the capacitor voltage direction cannot change instantaneously, so based on definition that we learned in the summary just now, the current direction through capacitor should be labeled as in this figure. So it means that the voltage over here, if this capacitor is initially charged, means that we're gonna have voltage polarity like this. So we cannot change this polarity. Okay, that's why the current of IC over here is flowing towards downwards over here, and current flowing through R or flowing through the resistor or IR is in this direction. So that's why the direction looks like this. That is because the voltage, initially voltage across the capacitor cannot change, the polarity cannot be changed instantaneously or abruptly. Okay, now we try to analyze the circuit. If we have this kind of circuit arrangement, okay, since the capacitor was initially charged, we can assume at t equals to 0, the initial voltage is V0. Okay, is V0. So what happened over here, we substitute t over here as 0. T V of t, okay, at t equals to 0, this is the initial voltage mentioned over here. Okay, this is initial voltage. And if we're applying KCL at the top node, so if you're applying KCL over here, we know that IC plus IR is equal to 0 because at this node, there are two current flowing out. Both are current flowing out, means that this is I out equals to I in. I in equals 0, no current coming in. So, and lead us to first order differential equation. Remember, just now I mentioned about IC, current flowing through capacitor is given by C dV over dt. Okay, using this definition, it will lead us to this kind of differential equation. Okay, and later on, by rearranging that the equation that we found over here, by rearranging this one and try to do some integration over there, we will end up with this equation where we have ln V equals to negative T over RC plus ln A. And after that, we try to taking power of E both sides. We put E over here and put E over here, and we will end up with equation, or the solution will be given like this: V of T equals to A E negative T over RC. With the initial condition, we know that this A, this A is given by V0. Okay. Now, the final equation of voltage across here, of voltage across the capacitor is given by V of t equals V naught E minus E over RC. So this is something new for you guys. You know that this is exponentially, exponential decay of the voltage over here. Why it is decaying? Because we don't have any voltage supply in our circuit. So the voltage is decaying from V naught towards zero value. If you substitute this t equals to infinity, this one will be equals to 0. All right, we get into here. We already finished over here. We get into here. The results show that the voltage response of RC circuit is an exponential decay of the initial voltage. Since this is the response of the circuit without any external voltage or current, the response is called a natural response. I think this statement I already mentioned you just now. It is an exponential decay of voltage response across the capacitor that we've seen in circuit earlier. And here we know that this is something also new. Here that you have tau over here. Tau here is given by is known as the time constant and given by value or the product of value of resistor and capacitor R times C. All right, maybe we get into this slide to get to know better about tau. Okay, time constant or tau, okay, is the speed at which the voltage decays and can be characterized by how long it takes to for the voltage to drop to 36.8% of the initial voltage. So this is what does it mean by the time constant or tau. In other words, if you don't remember, it's also okay lah. But if you in the following years, maybe in your second years, third year, maybe you will remember later on. The time constant, given that the circuit is RC, okay, time constant equation, remember here, time constant equation is not always given by R and C. Okay, for circuit involved inductor, the equation, the formula for time constant a bit different. However, here, if we consider circuit involve resistor and capacitor, the time constant is given by this equation. And the voltage response, okay, Vt, that I mentioned earlier over here, voltage response is given by V of t equals V naught, or this is initial voltage, times e to the power of negative t over tau, or t over r times c over here. Right. Are you okay so far?
Okay, Dad.
All right. Now, once we get to know the voltage response across this part, we can calculate what is the value of IR, maybe energy and so on, using this equation. Because with the voltage known, we can find the current of IR over here. And also, if you try to find IC, you need to use the formula that I gave for you over here. C equals to dV over dt. You need to differentiate this equation and multiply it with C. Okay, for here, if you try to find what is power dissipated in the circuit, power only dissipated at resistor. Power will not be dissipated at this capacitor, because this capacitor only stores the electric field, stores energy. And dissipation, power dissipation only happens across this resistor. So to get to calculate the power dissipated across the resistor, you will use this formula where PT equals to V naught squared divided by R. In other words, what gonna happen over here is we try to use V squared over R. V squared over R. Remember that our V is given by V naught E negative T over tau. If V squared means that V naught squared E to the power of negative 2 T over tau. So if we square this one, this is what's gonna happen. This is the answer or here, like this. All right, and for power, you know that formula of power is given by V squared over R. So just put in the resistor value over here. That gives us the value of power. You can also use I squared R, but I think this is the easiest way because the voltage is known. You don't need to find the current. If the question asks you about current, maybe you can also find the current. If you look at this current equation, also the same. If you work out the I squared R for power, it will give you the same answer as this. So I think it's easier for us to take the voltage equation and square it to get power dissipated across or in the resistor. For the energy absorbed, you try to use here is 1 over 2 CV naught squared times 1 minus E to the power of 2T over tau. Okay, if you want to know the details on how this equation turn up, you can always get into your textbook, but I can give it briefly that this is based on the integration of our power dissipated with respect to time. So if you integrate this equation with respect to time, you will get the energy absorbed by the resistor. And if you look at here, if you consider time is equals to infinity, okay, time is towards infinity, means that the energy absorbed by the resistor should be equals to this equation only. This equation is equals to 1, the time to infinity, 1, and this is the only or the equation of energy absorbed by the resistor is given by this equation. And if you remember back our summary, this equation basically is the energy across the capacitor or energy at the capacitor. Right. Okay, in summary, maybe you see that that's a lot of mathematics, advanced mathematics involved if you try to analyze RC circuit. Yes, of course, but you may find simpler way in order for you to get to analyze your circuit. This is the key of to solve your source-free RC circuit. The first one is start with initial voltage across the capacitor. If you know what is the initial voltage, means that VO in this equation Okay, VO here, solve. Okay, and second one, um, try to calculate the time constant. Try to calculate the time constant means that if you know what is the time constant, then you get the voltage response correctly. I mean, the full response of the voltage across the capacitor. With these two items, the voltage as a function of time can be known. Of course lah, both initial voltage and time constant, that's just that two parameters that we need to know to calculate the voltage function. And from the voltage, and then if you try to find the currents and you start finding the current based on that the voltage that we found earlier. And also, and the last point here, the resistance of the circuit is often the Thevenin equivalent resistance. Means that you need to know how to determine the Thevenin equivalent resistance. Here, you see that the circuit is as simple as capacitor and resistor. This is not the case that you will find in your assessment. And you will not on the assessment, in your exercise as well, you will find that the circuit will involve a lot of or maybe several resistors, maybe also several capacitors. What you need to do is you try to combine all the resistors and all the capacitors so that it will looks or it will end up forming a circuit looks like this. You're going to have a single resistor and a single capacitor. It means that if you have a few resistors over here, the value of R here is denotes as R equivalent. R equivalent is the value of R Thevenin in the circuit. And if you have a few more capacitors over here, you need to combine the capacitor. And the way to combine the capacitor, I've already put it in a summary. Maybe here you will see that if you have a series combination of capacitor, the way you combine is like the way you combine a parallel connected resistor. And if you have parallel connected capacitor, for example, C1 and C2 is connected in parallel, the way you combine those two capacitors is just by combining a resistor in series. So that's how we combine capacitor and capacitor and resistor. Okay, the resistor should be in a Thevenin value or a combination of several other resistors, as well as this C. Once you set up this kind of circuit, you can simply use these two equations to know to write down your voltage across these 2 points. And the voltage is given by V naught minus E to the power of negative T over tau. And here we have tau, which can be calculated using these two values, R equivalent and also C equivalent over here. But normally in your case, I think I just put one value of C. You don't need to combine C. Only you need to find what is the combination of several resistors over here. Okay, you can use these two equations in order for you to know what is the value or what is the response equation of these 2 points of voltage across this capacitor. Same goes to source-free RL. Okay, source-free RL, if you look here, the way we try to solve is the same like we see in RC circuit. However, here the value of interest is the current through the inductor. And again, we will start our analysis by looking at the initial current passing through the inductor. And please note that for capacitor, the voltage cannot change instantaneously. For inductor, current direction cannot change instantaneously. For example, if you have a current in that direction, okay, you cannot change the direction of this current. Only the polarity of this voltage drop can be based on the current direction. Based on this current direction, we're going to have positive, negative over here for VR and positive, negative of VL across the inductor. So this is for inductor. You need to set up a circuit which is look like this. And starting from here, you try to apply KVL around the loop using the definition of voltage drop. So here we have VL plus VR equal to 0. And remember that earlier I mentioned about equation to calculate voltage across the inductor. It is given by L di over dt. Okay, have a look at the summary that I put earlier. So applying the KVL around the loop will give us this equation, and after some mathematics of integrations, maybe simplification and so on, you will end up with these two equations where you're gonna have equation of current response where it gives by it gives as I naught times e to the power of r t over l. Here, if you look back at our RC circuit, over here consists of tau. So tau for RL circuit is given by L over R. Okay. This is example 7.1, example number 1. But I think I want to stop the class now because I need to attend the conference at 10:15. So far, do you have any question about what we have learned up until source free? We didn't describe or we didn't have a look at the example yet. Maybe you can look example 7.1 also available in textbook. Have a look at what's going on in example 7.1. Later on, maybe on Thursday, I will try to go through just a quick go through on example 7.1. You need to get read first example 7.1, and on Thursday we will discuss this one very fast. Okay, also example 7.2, example 7.4. I also have the example 7.1, 7.2, 7.4 over here. For those who don't have the textbook, maybe you can also look over here. But I really suggest that you go through your textbook for you guys to have a better understanding about this example. This PDF file I will put in e-learning later on, maybe after the conference. Now I think it's not enough time to do that. Anyway, you have any questions so far? I'm sorry for stopping this class as early as this point, because my session start about 6 minutes from now. Any questions so far?
No, it's okay.
Okay. All right. We'll meet again on Thursday. Please have a look at example 7.1, 7.2, and 7.4 in advance so that you have a better idea on what's going on. Although this chapter is not included in your test, however, the way we understand the circuits maybe benefit you guys in order to answer test one. So it's not like something useless, and I don't want to do the revision on this because it is not included in test one. Believe me, it's if you have a look at it, maybe you have better understanding on how do we use or how do we use the tools that we learn to solve other problems. Okay, I think I will stop now. Oh, already